Okay, so today I'm going to go over group work that covers chapter 10 and 11, and that is going to focus on radical reactions, reactions of alcohols and ethers, and then there's a little bit of a review for the final at the end. Okay, so what strategies have been helpful for studying for previous exams that you'll use to study for the final? I honestly recommend you do a lot of practice problems. The multiple choice questions from your old exams are going to be really helpful, as well as from your, if you want to look over your quizzes, that will have the major concepts. And then once you've reviewed the major concepts and done some practice problems for each chapter, then I recommend you do a practice exam. And I recommend you do the practice exam as if it's the real thing, like wake up when your exam is going to be, take the 2-hour final, practice final, and then go through and for each question you got wrong, mark down what concepts that tested over and like try to identify what your weaknesses are based on that, and then use more time to study those particular practice problems. So that's kind of what I recommend to study for the exam. And then also, of course, you can go check out my TikTok. It's at Organic Melissa, and I have a virtual organic review that I've been posting slowly over the past several days that can help you out. And then there's also all these other videos. And for my students, I have a review for every chapter listed out on the final exam review materials and questions that my students generated as well. So there's a lot of resources for you to hopefully help you succeed. Okay, so draw a diagram of all the ways to make alcohols. You can do this however makes sense to you, but the big ones that you need to hit are acid catalyzed hydration of an alkene. And actually, when I think of this, this is the big 3 ways to add alcohol across water. I have another video about that, or add water across a double bond. I don't know why I just said that, but if you have this double bond and you add OH on one side and H on the other, there's 3 ways to accomplish that. You have to pay attention to the regiochemistry, so is it going to add to the more or less substituted side? And more is Markovnikov, less is anti-Markovnikov. And you also have to pay attention to stereochemistry. Do they add on the same side? That's syn. Do they add on opposite side? That's anti, or you can get a mixture. So acid catalyzed hydration is 1. It gives you Markovnikov, and it also risks rearrangement because it goes through a carbocation, and it also gives you a racemic mixture. Another one is hydroboration oxidation. And that adds anti-Markovnikov. It's a syn addition for the stereochemistry. And there's no rearrangement that you have to worry about. And then oxymercuration, demercuration. And that adds, you actually get a mixture for the stereochemistry, but it adds Markovnikov, but with no rearrangement. And then another one is you could do an SN2 reaction with hydroxide as your attacking group, and you could do an SN1 reaction with water as your attacking group. So those are some options for you. You can do this diagram however you want. I like to do, my alcohol in the middle, and I'll have like, if I could do this starting material, this starting material, this starting material, that's an option for you. Or you could do a chart. I saw somebody does like synthesis charts where it's like, here's all the different ways I know how to make an alcohol and all the different things I know about it. So that's helpful too. Oh, also you can do the diol addition, which is osmium oxide in cold KMNO4. Either one of those, either osmium oxide or cold KMNO4 will give you 2 alcohols. And then another one is if you do Br2 with water, that's a halohydrin, that forms an alcohol as well. It's not just an alcohol, it's a bromine and an alcohol, but those are kind of some special cases. Okay, so whatever works for you, if you want to make a chart of that makes sense, we want you guys to do that. Okay, and then now all the ways to make ethers. There's actually less ways to make ethers, but they're still important. So one is Williamson ether synthesis. And this is actually just an SN2 reaction. I don't know why they give it a special name, but you have one ethoxide and one thing with a good leaving group, and you do an SN2 reaction and it gives you an ether. Two is if you want like a symmetrical ether like this, you can do acid catalyzed dehydration of alcohols to give you a symmetrical ether. The next is you could do alkoxymercuration. Demercuration, which is just using instead of water as your solvent to make your alcohol, you can use alcohol as your solvent, and that makes an ether. So basically, it's just like this reaction, oxymercuration, demercuration, but instead of using HGOAC and water, you use HGOAC and alcohol. Another one is the asymmetrical acid catalyzed. This is really not useful. I spelled that way wrong. This is really not useful unless you have a tertiary. And the main reason for that is if you have two alcohols that you're trying to go through the alkoxy or the acid catalyzed, if it's not symmetrical, you're going to get a mixture. Say you have this group and this group. So you'd get some where there's two of these on each side of your ether, some where there's a mixture, and some where there's two of these on each side of your ether. The exception is if you have a tertiary alcohol. This actually does work really well because it can undergo an SN1 reaction where your leaving group will get protonated and then your leaving group leaves. And so then you have a tertiary carbocation plus this alcohol, and then that can come in and attack. And the tertiary carbocation is so much more likely to form that this works well in this situation. And the very last thing is if you do a halohydrin formation with alcohol, that will also make an ether, but it's kind of a special kind of ether. It gives you Br and an ether on the other side. Okay, so I would make this ether, if I was going to make this ether, this pretty much the only way to make this tert-butyl ether like this is if you actually do these reagents that I did here in the example. You can't do an SN2 to make this because if you made your nucleophile this group, hopefully you remember, that will favor elimination. And if you make your nucleophile this group, but you have a tertiary leaving group, whatever that is, that's going to form a carbocation, not going to leave. So this would also favor elimination. So you would not get a substitution reaction from that unless you did an SN1. So this by SN1 would give me the product that I want. Okay, the next question, predict the products of the following reaction. If you have an alkene and you react it with any peroxy acid, so MCPBA, or this with 3 oxygens instead of just 2 like a normal carboxylic acid, that's called a peroxy acid, or sometimes I'll just say peroxy or per acid, it will make an epoxide, and it retains the stereochemistry. So if this one's going up and this one's going down, there's cis and trans, then we're going to keep cis and trans in our epoxide formation. So here we don't have the stereochemistry drawn. There's 2 hydrogens, but the first step will be formation of the epoxide. So that's the first step. The second step, you have 2 options when you have an epoxide. It's acid catalyzed ring opening, or you have a basic nucleophile. So they sometimes call that base catalyzed. So this strong nucleophile is going to actually basically do an SN2 reaction, and it's going to attack the least substituted side. And the way I remember that is SN2s will attack the least substituted side. You know that from all of the reactions we've done, but also blam. Base attacks the least substituted side. Acid attacks the more substituted side. So this nucleophile will come in and attack on the less substituted side, just like if it would if it were an SN2. And this will break open. And you'll get, and I always try to number 1, 2. So this is 1, this is 2. Right here is where the ethoxide came and attacked. So this bond is formed between 3, 4, 5. That just kind of helps me number. And then also the bond between the oxygen and carbon 2 broke. So there should be an oxygen on carbon 1. And that's O minus because it took the electrons in this bond with it. So now there's 3 lone pairs around this oxygen. Okay, so normally if you have a reaction like this, the next thing you'll see is they'll add acid to turn this into an alcohol. That wasn't included here. That's my bad. I should have included that. But so this would normally be your final answer. If there's no H+, it'll stop at the ion. Now, how would this reaction be different if ethanol was used instead of ethoxide? Well, actually, ethanol being used instead of ethoxide is going to mean that you'll also need acid to open this. So no reaction would take place without acid. So acid is needed to catalyze this. So if we had acid and alcohol, the first thing that always happens when you have alcohol with or oxygen with a proton is it's going to protonate. So we get OH plus. And then I like to think of this reaction as SN1 light. It's like similar to SN1, but not exactly like an SN1 because this leaving group doesn't leave initially. It does seem to happen all in one in SN2 form. However, so there's no rearrangement. A full carbocation doesn't form, but there is a partial positive here. That's where this nucleophile is attacked and then is attracted to, and then the ring will open up from there. So you get your O, that still has this ethyl group with an H+, and then over here you have an OH. So then the final step is it would need to go through deprotonation. And you would get this. Ran out of space there at the bottom. Just make sure you don't lose track of your carbons. That's the main thing that happens whenever there's ring opening reactions is people will lose track of their carbons. So make sure that you keep track of the number of carbons in the epoxide ring. And I think you're likely to open next semester spending more time working on that. Okay. Oxymercuration, demercuration. So normally we see oxymercuration, demercuration to get alcohols, but if you have alcohol as a solvent, this is actually an alkoxymercuration, and it's going to give you an ether. So the same initial transition state will form with HGOAC. And hopefully you just recognize this as one of the big 3 ways that we talked about at the beginning to add alcohol or an ether across the double bond. So you'd get that transition state. I'm not going to draw all the way out, but I do have a video where I talk about the mechanism. And then your alcohol will come in and attack on this side, breaking that bond. And you end up with O, CH3H, and that's positively charged. And then on this side, you have HGOAC, but then the HGOAC, this step, they add anti to one another. But then the HGOAC is replaced with NABH4, and your methyl group is deprotonated. Your methoxy group is deprotonated. So actually you'll get a mixture of products. You won't just get the H and the OH as wedge and dash. You'll also likely get wedge and wedge plus the enantiomers of both of these. So you'll get a mixture of products for that, but you will get overall your methyl group added to one side and the hydrogen added to the other. This next question is mesyl chloride with pyridine. And I hope my students remember what this does. This is actually a way to turn an alcohol into a good leaving group. So if you have OH and you react to a tosyl chloride or mesyl chloride, so tosyl chloride looks like this. And then you have this Cl with it, or mesyl chloride is this one. And I just write OTS, OMS, or I even sometimes just write good leaving group like LG there, just to keep that straight. And the important thing about this reaction is this does not invert stereochemistry. So you turn this into a good leaving group and it doesn't change stereochemistry at all. If you use something like PBr3, it will turn it into a bromine with inversion of stereochemistry. So that's important to look out for. And then the next step is reacting it with this ethanol or methanol. And if this is a good leaving group, the leaving group will leave. I guess I should say, I'll ask myself, is this acid-base, SN1, SN2, U1, E2? And if I see methanol in a good leaving group, that makes me think substitution or elimination. And then if it's a weak nucleophile, it's not negatively charged, it's neutral, so that makes it a weak nucleophile. So it's going to favor the one side, and it's narrow, and there's no heat, so I'm thinking this is going to favor an SN1 reaction. So that's how I know the leaving group is going to leave. I guess technically this can just be a straight line because it's planar now. And then this will come in an attack, and it adds her on both sides. So you'll get OCH3. It initially is protonated, but it'll be deprotonated. You'll get that, plus you'll also get the wedge and dash opposite of that. This stereochemistry on this carbon won't change, but this, you'd get this plus the enantiomer of just this carbon. So these two will swap. You'd get these as your final products because it can attack from either side. But your methyl group won't stay the same. So these are diastereomers of one another. Okay, now this next question asks, oh, I already talked about that. How would the reaction be different if PBr3 would be used rather than mesylate? So initially, when your PBr3 attacks, it switches your alcohol into a bromine. And I've already worked the reaction mechanism for that in an earlier section. So go back and check that out if you want to see the reaction mechanism there. But essentially, it's an SN2 reaction where the alcohol is turned into a good leaving group, and then the bromine attacks and kicks it out. So your stereochemistry is inverted. And then if you go through the next step, which is again an SN1 reaction, actually after that, it would be the same because you get the carbocation. So from there, you get the same final products. Okay, draw an example of each of the following types of radicals and then rank them. An allylic radical is one away from a double bond, and this actually can partake in resonance. So if you take one electron from this bond and the radical over here, you'll leave behind a radical on this side. So the radical is really dispersed. There's a partial negative or a partial radical all the way across, rather than it be concentrated in one area. So that's the allylic. A secondary just has a radical on a carbon that's touching two carbons. A primary has a radical on a carbon that's touching one other carbon. A tertiary has a radical on a carbon that's touching three other carbons. A benzylic is actually, if you have a benzene ring, it's one away from the benzene. So it's right here on this group right here. And this also undergoes resonance. The radical can move around the ring. So there's actually a partial radical here and here and here. So that makes it much more stable. And then a methyl would just be CH3 with a radical on it. One that I didn't put on here that I wish I kind of had is a vanillic radical. And that's when it's right on the double bond. And that does not really occur very often at all. It's just not stable. So if I'm ranking these, I would think benzene is going to be the most stable because it has so many options for resonance. followed by allylic because it has one option at least for resonance, and then tertiary because the electron density can kind of stabilize that radical, and then secondary, then primary, and then methyl. So actually, I'll draw the methyl like this. So that would be how I rank those. And actually, they've done studies to determine if this is true, and this is the proper ranking order of stability. Okay, and now let's get into radical reactions. So this is more of chapter 10. Okay, so how do I know this is a radical reaction? Well, it's not an acid-base reaction because there's no base or acid. And it's not going to be a substitution or elimination because there's not a good nucleophile or a good leaving group. It doesn't look like it's something from chapter 8 because there's no double bond where this can be added to. And it's not an alcohol reaction or ether, so there's nothing that I can do from chapter 11 either. So the only thing that's left is kind of got to be a radical reaction. The other hint to that is if you have an alkane with nothing on it, radicals are a good way to make those useful in reactions. So usually they'll use radical reactions to make them into halogenations. The other thing is you've seen Br2 before with an alkene, but if it has some kind of radical initiator, so this would be H-nu, so that's light basically, or heat, it will form the radical. So look for Br2 with light or heat, or peroxide with light or heat, and that will form your radical. And what happens in the first step, I don't know why I just drew this here. What happens in the first step is the heat or the light will react with this bromine to make it into two radicals. And radicals are exactly what they sound like. They're radical. They're trying to react. They're trying to get all up in everything and like make changes happen. You know, it's like when they talk about radicalized people in politics. I won't get into one side or the other, but radicals are also trying to radicalize things and change things. So they will react quickly with whatever they can get their hands on. Now for bromine, it's a little bit more stable of a radical. So it is going to try to get its hands on something that will leave behind a radical that's more stable. So in this case, this bromine will come and try to take this hydrogen because when it takes one of the electrons from this bond with a hydrogen, it's going to leave behind a radical. So one electron from this bond goes to meet up with the HBr here. This electron goes to meet up over there. It's like they're going on a date. These two are meeting up, and then somebody gets left behind. And so that one radical that gets left behind, that also is looking to go and react as much as it can. So it will likely keep reacting and continue to propagate, but eventually a termination step will take place. And so we used one of these bromines right here. The other one is still for grabs. So I'm going to take that bromine plus this radical. I don't know why this looks crazy. These two are now they found each other. They've both been broken up with, a radical's been left behind, and now they found each other. And it's always going to be the most substituted or most stable position, either the benzylic, allylic, or the most stable after that it can get its hands on, that the bromine is going to form. And so you can go through all these steps every time if that helps you, but as you get comfortable with it, you should be able to quickly look, oh, bromine with light, this is going to make a radical reaction. It'll form the most stable radical. That's where my bromine's going to go. That's kind of what my process is when I look at something like this. Now, if this was a chlorination, chlorinations are way more reactive. And so if you had a chlorination, it would likely give you a chlorine there or a chlorine here. It's going to be not necessarily just at the most stable position. You would hope it would be more stable, but it's most likely that you'd get more variety of reactions if you have chlorine rather than bromination. Okay, this is more chapter 11 again. Which of these would have the weakest intermolecular forces? I think the weakest intermolecular forces are going to be the ones that don't have hydrogen bonding. So I'm seeing this hydrogen's available, this hydrogen, all of these are available to have hydrogen bonding take place, which is really a super strong dipole-dipole intermolecular force. This does have a dipole-dipole intermolecular force, but it's not with a hydrogen bonding available. So this would be the weakest intermolecular forces. And that also means that has the lowest boiling point, because intermolecular forces are basically like I have two molecules and how tightly are they held together. Now hydrogen bonding, they're held together like this, so it's hard to break them apart. So it's hard to get the molecules to separate out from a liquid into their gaseous state. If they're just holding on like this, it's much easier to separate them out and get them from a liquid to a gas in their boiling point. So weaker intermolecular forces is a lower boiling point. Now water solubility is a little bit different. Initially, I had this question written as which of these would be soluble with water? And the answer to that is all of these have some level of solubility with water. But then I wanted you to think further about which one would have the least solubility in water. And honestly, I think typically an ether would have a really low solubility in water compared to an alcohol that's similar. But I think this alcohol would also have pretty low solubility because it has a big bulky group that is not going to be able to interact with the water very easily. And then same thing here, there's a long carbon chain that's not going to be able to interact with the water very easily. So I think that this ether would probably have the lowest solubility, but I don't think these are going to have great solubility in water either, honestly. So I really wanted you to think through that idea and ask yourself, like, how do these different oxygens and carbon chains interact with water? And that shows a deep understanding of organic chemistry. Okay, now we're predicting multi-step reaction. Here we have Br2 with H nu. So this is an acid base. It's not a substitution or elimination. It's not an addition because we don't have a double bond to add to. There's no alcohol involved in step 1. There's an alcohol in step 2, so that gives us a hint for there, but there's not one in step 1. So, and it's with a radical initiator, so I know this is going to be a radical reaction that forms right there, and then the bromine will go right there. Boom. So that's our first step. The next is just in the presence of an alcohol. So then let's start back over. Is this acid base? Well, oxygen can sometimes be protonated as an acid base, but not really. Is it going to be a substitution elimination? Well, we have a good leaving group and we have a nucleophile, so I think yes. Not only do we have a good leaving group, but this is a tertiary, so that gives me kind of a hint that it's not going to be SN1. So, or not going to be SN2, I mean. So let's look at our nucleophile. Is it strong or weak? If it's strong, if it's negative, then it goes to the 2 side, but this isn't negative, this is neutral. So this is going to go to the 1 side. It's going to be SN1 or E1. And so then we don't have heat. This isn't bulky, so there's nothing really tending it towards E2. So I think this is going to be towards E1. So I think this is going to be SN1. Honestly, usually if you have SN1, there's going to be some E1 too. So it's not perfect, but this is the majority project I think would occur. This oxygen would come in and attack. And you'd have initially your protonated ether, but if you keep reacting it, if you put water, it'll scavenge off that proton and you'll get your ether. And that's your final product. Okay, now the next question, HBr and peroxide. So all peroxides does is make your traditional Markov-Nikov HBr addition go anti-Markov-Nikov, but I'm going to show you. Normally, if we have HBr, the first step that happens is always the alkene attacks, and the hydrogen will add in such a way to give the most positive carbocation, and then the bromine attacks. So this is what happens if you don't have peroxide. Sorry, that looks terrible. This is what happens if you don't have peroxide. However, if you do have peroxide, the bromine is actually going to attach first, giving you, you'll get an initiator, make a bromine radical. That bromine is going to react with your alkene to attach your bromine and leave behind this radical, and your hydrogen that was left behind up here will combine in the termination step. So due to a radical reaction, HBr with peroxides just does anti-Markovnikov on your traditional HBr. So this is your answer. This is what it would have been if you didn't have peroxide. So you don't have to go through those steps all that time. If you just kind of remember what it does, that might be easier for you. Okay, and then we have question 7. This gets into our general review for our exam. So if you're looking at these structures right here, it asks you to rank them based on the bolded hydrogens from most acidic to least acidic. So we know the pKa's of certain functional groups, so how willing a functional group is to give up its proton. So we can estimate the bold-faced hydrogens based on pKa's. So usually an amine pKa is 38. So I'm going to say this is probably close to 38, honestly, because it's substituted. Usually substituting out hydrogens for carbon chains makes it a little bit more basic than that, but all these are in similar boats. So the next, carboxylic acid, is usually 4 to 5. If you have it on an alkene, it's usually 45. If you have a hydronium ion, so you're not looking at alcohol for this, you're looking at something that has 3 things bonded to an oxygen that's also positively charged. So that's more like a hydronium ion than water. And hydronium is actually negative 1.7. A lot of times I'll see students do that and they're like, oh, water, it's 15. But water is not similar to this because water doesn't have a positive charge and an extra hydrogen that's trying to get rid of. So you need to make sure to look for that. And then an alkyne, this pKa is 25. So this is going to be the most acidic, and then this, and then this, and then this, and then this. And that's how I would work that question. Okay, next question, be able to draw all the resonance structures of the following molecules. So when we draw resonance structures, the big thing is to look for areas of high electron density if it's negatively charged and see how that can move around in the structure. So if I were to take this extra lone pair here, if I drew an extra bond as a result of that, there would be 5 bonds to this carbon. Carbon doesn't like 5 bonds, so then we have to do something else. And a key thing that you can do usually is break a double bond and just leave a lone pair where it was, so that that carbon is fully satisfied in its octet and you don't have too many bonds to the carbon. So if you did that, if you just moved those 2 structures, you'd end up with this. And you have to ask, is this a legitimate Lewis structure where there's 1, 2, 3, 4 things bonded to this carbon? There's 1, 2, 3 in a lone pair, so nothing has too many bonds to carbon, so we're good. So then we have to ask, is there anywhere else that this electron density could be shared? And there's really only 2 options. Either you could go here, but if you did that, there's 3 hydrogens already, so a double bond there would be 5 bonds to that carbon. That's not great. The other option is to go here. And if you went here, there is a bond you could break so that there wasn't too many bonds to any individual carbon. So if we did that, there'd be a new bond formed here, and what was this double bond broke and became a lone pair. And you really aren't going to be able to do resonance by watching me do it. You have to practice this on your own and ask yourself, like, are there enough hydrogens? And once you've practiced it a lot, it will come a lot more natural to you. Okay, and then RNS configuration with stereochemistry. So you label the highest priority. Highest priority is the thing that's directly attached that has the highest molecular weight. So we have an oxygen and 2 carbons. So that's 1. And then now we have 2 carbons, so we have to compare these, what they're attached to. So this carbon has 3 hydrogens. This carbon has a carbon-oxygen hydrogen, so this one wins. So if it's going to the left at the top, that's S configuration. And you just connect 1, 2, 3 and make sure that the hydrogen is pointing backwards. Now on the bottom, they actually have the same priorities, 1, 2, 3. So you'd think that would be R, except the hydrogen is pointing towards us, not pointing backwards, so we have to flip it. So this is an SS configuration. So if you want to take this question a step further, you can draw the enantiomer, and you can draw a diastereomer, and there's a good bet because each of these have carbon, alcohol, and hydrogen, that there might be a meso compound. And you can see if you can identify a meso compound. Usually meso compounds have to have a plane of symmetry, and they have R and S configuration. So that's just a way to take this group work a step further for you. Okay, well, I hope that was helpful for you in solidifying some of chapter 10 and 11 and in getting ready for your final. And if you have any questions for me, please feel free to reach out. I want to help you guys succeed. And check out my review that I have on TikTok. I've linked it below, and I've linked other other videos that I think will be helpful to you as well. Happy studying!